On the oscilloscope, we have a nice image of the time constant of an RL circuit exponential decay. So now that we have that, it's possible to measure the time constant by looking at the time on the oscilloscope and how the voltage decays. So before we do that, we'll look at the math really quickly. So we have our RL circuit right here, and we're assuming that we have a unit step input. So that steps from 0 volts to 1 volt at time t equals 0, and that's displayed on the oscilloscope right here. That's our step. And if we look at the equation, so the voltage across the inductor, which is what we're measuring with the green trace, is going to be equal to what I usually call the displacement voltage. And so if you think of the step function, it goes from 0 to 1, so the voltage is displacing by 1. So if we just say that delta V there, it's going to be multiplied by e to the minus t over tau, where tau is the time constant. And we know the time constant for an RL circuit is going to be L divided by R. And if we put that into this equation right here, so our delta V is 1 times e to the minus t R over L. Now if the time constant, thinking back to the t over tau right here, equals t, right, then we're going to have, this is going to equal 1, so we're going to have e to the negative 1. So e to the minus 1 equals 0.37. So that's saying that when one time constant of time's gone by, that this value for the e is going to be 0.37. So if we go back to this equation right here, so 1 times 0.37 equals 0.37. So what that says is that if we draw a graph right here, if this is t0 equals 0, we have our exponential decay. That's the output of VL. And we're starting at 1 volt right there, and we're decaying down, asymptoting to 0. It says that after one time constant, in other words, that value of L over R in seconds, we're going to have decayed to 0.37 volts. And that's how we could figure out the time constant easily on the oscilloscope looking at the step function. So if we go back up to the oscilloscope over here, you can see we have that waveform. And we discussed previously that the inductor is not ideal, so it doesn't quite actually make it up to the value of the step as it should. It's a little delayed in time, shifted, and attenuated because of the parasitic capacitances and resistors in the circuit of the inductor. So what we could do is we could pretend, really, it's sort of a good approximation. It'll work for this lab and for some basic things. We could pretend that the inductor voltage actually makes it to 1 volt. I'm trying not to touch the screen because it's a touch screen. And it decays from that 1 volt, and then it exponentially decays down as it asymptotes to 0. If I change the time scale, you can see that that's happening right there. But I made the time scale small, so that way I could see close what's going on. So there's a feature called a cursor on this oscilloscope. And with the cursor, you could drag these lines over right here. And so the lines on the horizontal axis could mark out time. You really want to move the whole waveform. There we go. So with these, I could calculate the time between, or the oscilloscope will actually calculate the time between the X2 marker and the X1 marker. There are also Y cursors. If I could grab that, so I could move that one, say there, and I have the other Y2 cursor right there. So we know that our step function is going from 0 to 1 volt. So the first thing I'd want to do if I'm trying to find the time constant, like I'm trying to find the time, I know where the voltage is going to be after one time constant. It's going to be at 0.37, right? Because we're decaying from 1 down to 0.37 volts. So if I look over here, I could actually set that. Let's see if I could, no, can't use that knob right there. I thought that knob worked to turn the cursor, but it doesn't apparently. Go away. Okay, so what I'm trying to do is set the Y2 value equal to 0.37, or 370 millivolts. And there I'm at 372 millivolts, probably close enough for what we're trying to do here. So now I find where that voltage intercepts the inductor voltage, the green curve, and I could drag the second time cursor over there. And I have those two intersecting right where all those three lines intersect. So we measured the decay of the voltage, and now the time it took to get to that decay, which is 37%, or one time constant. So if we look at the delta t, or sorry, well, here it's delta x, it says that we're at 16.5 microseconds. So 16.5 microseconds. And now, if I know either the inductor value or the resistor value, I could calculate the other one. But for now, we know that tau equals 16.5 microseconds, and we could figure out the value of the resistor or the inductor. We couldn't figure out both of them if they're unknown, but if we knew one, we could figure it out.